Hello, everybody. Today we're going to be talking about a new 3D printing method that's being developed, and it's one that, compared to older methods, is able to produce more and intricate parts in much less time. So it's a very promising new technology. So what we're going to do is we're going to go through a little bit of background information, the purpose of the study, the methods the researchers used, and then go over the results that they got. So a little bit of background information. So this study is about voxel 3D printing. So what is a voxel? So a voxel is it's you can think of it as basically a 3D pixel. So if you have a screen and the whole thing is made up of 2D pixels that are combined together to make one big picture, a voxel is essentially the 3D version of that. So you can combine multiple small elements into something big, and instead of being just a different color, those voxels could each be made out of a different material or empty space, so that you're building something from the ground up out of these tiny elements. And as the resolution gets higher, each tiny segment or voxel of a component can be independently controlled, which makes it very useful for producing complex parts that have different materials or complex geometries. So this is compared to some of the older technologies. The probably most common one is inkjet 3D printing, which essentially works the same way as a 2D inkjet printer, but it prints layer by layer and then cures each layer as it goes. So it's able to print with high resolution, but fairly slowly. And then the other common method is direct ink writing, or DIW, which is an extrusion-based method. So if you've seen 3D printers before, this is likely along the lines of what you're going to have seen, where it extrudes like a thin cylindrical filament through a nozzle, and it's able to use more materials than inkjets, but it's also very slow, and it switches between those materials very slowly, which limits its usefulness. So the study itself, they're trying to solve three problems. So the first one is the highly limited materials of inkjet and direct ink writing 3D printers. The next one is the low voxel resolution, because direct ink writing requires very large voxels, which naturally just limits the amount that you're going to be able to do. In the same sense as a screen, as the resolution gets higher, you have smaller and smaller pixels that are being formed into a more complex and more detailed like whole. You're doing the same thing with voxels, just in 3 dimensions. And then the last one is going to be the printing speed and the material switching speed. So both of the older methods are very slow in both of these. And so for the technology to be viable, we really have to increase the speed. So the method that the researchers used is something they termed multi-material, multi-nozzle 3D printing, which is a large mouthful, but it's exactly what it sounds like. It's a 3D printer that uses multiple materials and multiple nozzles. And it allows for a faster printing speed because it has more nozzles, so it's extruding more material at the same time. And the researchers used a pneumatic control system, meaning that it's controlled with air instead of mechanically with a motor or gears or anything like that, which allows for much more complex but also very capable control systems that can do stuff that a mechanical system would not easily be able to do. And this allows for much faster material switching. So a traditional direct ink writing printer would be able to switch materials approximately 1 time per second, so 1 hertz, versus this MM3D method that can do as fast as 50 hertz, which is 50 times per second. So to put that into perspective, a blink of an eye takes anywhere from 100 to 150 milliseconds. So with this method, they can switch materials 5 to 6 times in the time it takes to blink, which is clearly a great advantage. And then the large nozzle array allow many materials to be used at once. Each one of those nozzles can be extruding a different material, and the pneumatic control system allows that to be controlled very precisely. So to demonstrate this, researchers use 2 different demonstrations. The first one is a Miura origami pattern, which is it's a pattern it's got a very large surface area that can be condensed into a small volume, as you can see in the figure here. And that's very useful, especially in areas like aerospace, where something like a radiator or a solar panel needs to be able to be very small to be condensed into a small area and then expanded, because its usefulness is directly related to its surface area. So things like I said, solar panels or the mirrors on the James Webb Space Telescope might be a common example. So with this technique, they were able to print it out of multiple materials. So the white lines you see in that figure there are made out of a softer material, so they can fold. And then the orange areas are made out of a harder material to give it structure and perform the actual the function of it. And this is very difficult with traditional methods. It's doable, but it's going to be very slow. And one of the problems with traditional methods is the borders between the two types of materials are going to be very weak because they're not going to bond well together. And with this method, it creates very strong joints. So failure points on this design here are not actually at the points where the materials connect. It's just regular material failure that you would get in any kind of material. And then the second demonstration they used was soft robots, which is they're robots made out of soft materials, which makes them much more safe for human interaction, so they're less likely to harm humans. And it's useful in the biotech industry to create artificial body parts. And this part you can see in the figure here has rather complex geometry with overhangs and channels and different materials that would be very difficult to do with traditional methods, but was doable with this much faster too. And it, again, uses multiple materials. The blue parts in the figure are made out of a softer material, and the gray parts are stiffer, and that would be very difficult to do with any other method, but with this method it's very quick and easy. And it's, like I said, it's much faster, and it allows for much more complexity because a normal direct ink writing printer would have difficulty with overhangs and channels and things like that. And so the results of the study is they had some successful first tests. As a proof of concept, it was very strong. They did have some constraints. One of them was periodicity. So it might sound complex, but as you can see in the image here, the cubes or the voxels in that picture, they have a repeating pattern of the same color pattern repeated over and over. And the way this nozzle was designed, that has to be how it's done. So in future designs, they will have, hopefully, the goal is independent nozzles that can be controlled independently, so that each you're not constrained by that like repeating period, and you can extrude whatever material you want to extrude wherever. And then one other thing future designs will likely have is a higher resolution, so they'll have more nozzles, but they'll be smaller nozzles, so they're able to print with increasingly smaller elements, allowing for much more complex and useful parts. So in conclusion, the researchers used something called multi-material, multi-nozzle 3D printing to achieve this voxel 3D printing, as opposed to previous methods of direct ink writing or inkjet. And this allowed for a much higher material switching speed and printing speed over previous methods. And that allowed for much higher versatility and complexity of parts. And hopefully this technology will continue to be researched and improved in the future. Thank you.